Hello, dear students. I'm going to solve another AQ exam question. Though, so here is a that is a question related to tidal power and the potential energy and the work done. Okay, now tidal power could make a significant contribution to UK energy requirement. This question is about the tidal power station. So, in this question, in this video, we're going to solve the tidal power station energy, which trap the seawater behind the tidal barrier at high tide and then release the water through the turbines. So here is a tidal barrier. This one, this rectangle shape, that's like a vertical. This is a tidal barrier, and that there is a turbine here. The black color, that is a turbine. Okay, turbine can produce the electricity or electric power, and so here is a high tide. Okay, here is a high tide. Okay, so here the distance is 10 meter from this line to this center line to above is 10 meters, so it's below is, we can see that. So if we note the number of lines, we can see that 1 2 3 4 5 6 7, almost 6 to 7 is 10 meters, so it means these three lines, it gives us 5. So this is the halfway from the ground, half meter, 5 meters. So here is also the 5 meter from the ground, 5 meter from the ground. Okay. So now calculate the mass of water covering area of 120 meters. So area is given, that is 120 kilometer square. So we can convert this into meter square. 120 into 1 kilometer is 1000 meter, or 10 power 3. So 10 power 3 whole square. So we get 120 into 10 to the power 6 meter. So area is given. Now height or depth is given. Okay, so depth is given. Depth is equal to d is equal to 10 meter. So this the deep depth of this is 10 meter. So density of water is 1100. Density is 1100 kilogram per meter. Now we have to find the mass of the seawater. So simple use density equation. Density is equal to mass per unit volume. So mass is equal to density multiplied by volume. So first we have to find the volume. So volume is actually, we simply use volume is equal to area multiplied by the depth, because area has two sides and depth is the third side. So if we multiply length, width, and the depth or height, so uh, we get the volume. So we just multiply 120 into 10 power 6 into 120 into 10 to the power 6 meter square into depth 10 meter. So we get 120 into 10 to the power 7 meter cube. So density is 1100 kilogram per meter cube multiplied by depth. Volume is 120 into 10 to the power 7 meter cube. Okay, now we solve this 1100 and 10 power 3 120. Okay, now we solve and we get the answer that 1.3 into 10 power 12. 1.3 into 10 to the power 12 kilogram is the mass of the. Okay, now we move forward. Okay, here is the next question, that calculate the maximum loss of potential energy of the seawater in part 1. Okay, so we have to find the loss of potential energy seawater. Okay, now as we saw the, as we know that when this water goes through turbine, so it will release, turbine will release this water through, and it will go through the seabed, or it go to the down. Okay, now maximum is, it covers the maximum height of 5 meters. Here is the examiner has a trick. Okay, he gives the 10-meter height above the this turbine, but we know that the loss of potential is when this water goes utilized, and it goes to the seabed. Okay, now so here you can see that the loss of potential energy can be maximum loss of potential energy, because some waters are above, but we are not discussing the minimum energy they loss. Maximum they can lose energy when they reach to the bottom. Okay, when they reach to the bottom, and they cover the height of 5 meter. Okay, actually we need to know the height. Okay, 5 meter. So maximum potential energy, loss of potential energy loss is equal to mgh. We simply use mgh. So m is the mass that we have found, 1.3 into 10 to the power. We already calculated this mass, multiply g divided by 8, 1 multiply by height. Height is 5 meter. So we just multiply and we get 6.4 energy loss, that is 6.4 into 10 to the power into 10 power 13 joule. So this is the potential energy loss. Potential energy. Okay, now for the third part, the potential energy of the seabed released through the turbine calculated the lost over the time period of 6 hours. So the time is given. Estimate the average power the output. Okay, we need to find the average power output of the power station. So in order to find the average power, so we use the formula power average equal to, as we know that power is actually rate of doing work. Rate of doing work equal to power per work per unit time. Okay, so work is actually here, the work performed by this water is converted into useful energy. That is the energy, that is the potential energy lost, equal divided by time taken. So potential energy we already calculated, that is 6.4 into 10 to the power 13 joule, divided by time taken is 6 hours. So 6 hours can be converted into 6 hours we can convert with hour. 1 hour is 60 minute, and 1 minute is 60 second. Okay, so this 6 into 3600, 3600, so this is in second. Joule per second is a power, that is the watt. Okay, so average power we calculate by dividing this, that is the total power that turbine generates, which to power 310 power 6, or we can write in megawatt. 10 power 6 is 1 mega, so 300 megawatt. So average power is here, this is the total power generated. Okay, now as we know that this is given that power station efficiency is 40%, mean useful it can convert only 40% of this power. So we have to find the average power output, that is equal to total useful power that is converted into 40% of this value, 300 megawatt. So 40% of this value is, we just 40 multiply by 300 divided by 100 into megawatt. So we multiply this factor with the 40% and divided by 100, so we get the value of 300, that is 40%, that is 120 megawatt. So 40% of 300 is 120 megawatt. So useful power is, average power useful that is converted is 120 megawatt. Okay, thank you.